Hello everyone, I'm Prof.Joun. This final lecture for variational approach to FEM is on finite element equations and solutions. We will be taught how to construct the finite element equations and solving them. Also, we will try to understand the characteristics of finite element solutions. This slide shows an example of the sampling process of the finite element model we constructed already for practicing finite element analysis by hand calculation. In this equation, each color is for an element. That is, red color is for element 1, blue for element 2, and green for element 3. Finally, we obtain this finite element equation ready to be imposed essential bound conditions. But the node numbering is different. The resulting finite element equation becomes different, as can be seen here. To the contrary, element numbering has nothing to do with the finite element equation. However, the meaning of the finite element equation does not change because different node numbering changes only the order of unknown nodal values together with the position of their associated stiffness matrix elements and force vector components. We can see that the numbers of zero elements of the total stiffness matrix in these two cases of different global node numbering are the same. In addition, numbers of real values 1, 2, and -1 in stiffness matrix for the two different finite models are perfectly identical, which are 2, 2, and 6 respectively. Node numbering has an effect not on the final solutions but on the position of stiffness matrix elements and force vector components, which may affect computational time depending on the scheme of solving a set of linear equations. Therefore, optimal node numbering scheme depending on linear equation solver is employed by most software, indicating that just users of finite element software don't have to think much about detailed finite element techniques, which can be carried out automatically by the software, especially when a functional automatic finite element mesh generation technique is employed. Anyway, you'd better know common knowledge about some basic techniques. In this case, all zero elements are placed in the corners apart from the diagonal terms, and thus a banded matrix technique may be employed. In the banded matrix technique, the number of arrays needed is dependent on bandwidth of the matrix. That is, a maximum order for diagonal band involving non-zero element, when the order is calculated from the diagonal of this matrix. Okay, in this case, order 1 is the diagonal itself, and 2 for this diagonal band. Therefore, the bandwidth of this matrix is 2. It's just one conventional method to save the stiffness matrix. When we use a traditional skyline method, we save the elements of stiffness matrix and the skyline formed by non-zero elements. For example, I attach the order that is number in blue in the example matrix. You can see from comparison of this and this matrix that the number of arrays in the sky method is also dependent on node numbering. Sparse metric techniques are also inherently appropriate to solve the finite element equations. In these cases, only non-zero elements with their indices for address are saved, and the number of arrays needed is independent on the node numbering. We are now going to impose boundary conditions on the finite element equations. These are the finite element equations before imposing boundary conditions. The boundary conditions are given like this. That is, nodal values at both ends are all 0. Denoting this equation as Ku equals F, let's calculate determinant of the total stability matrix. It is interesting to note that it is 0. Absolutely right. It should be. It is because of so-called Riemann mode occurring before imposing boundary conditions. Because we know the nodal values at essential boundaries, we can just plug them into these FE equations by force. So sometimes essential boundary conditions are called first boundary conditions in FEM. We can rewrite this finite element equation in terms of unknown nodal values. Of course, we can eliminate unnecessary terms to make the final finite element equations more compact like this. This method is called elimination method. There is another way to reflect the essential boundary conditions onto finite element equations. That is so-called penalty method, which deals approximately with essential boundary conditions. Approximate imposition of essential boundary conditions is made by multiplying their associated diagonal terms and first components by a large real number. It is very simple, but relatively inefficient and inaccurate. This shows how to impose the essential boundary conditions in the penalty method. Now, on the left is the process of solving these final element equations. Solving these equations, we obtain all nodal values. These two from these finite element equations, and the left from essential boundary conditions. This figure compares the finite element predictions and the exact solution, revealing that superconvergence can be seen. That is, nodal values are all exact. It can be noted that a great difference of slope at light M, which is concerned with rate of heat conduction, occurred, even though the approximate solution can be more or less acceptable. The temperature itself is the primary state variable, which is calculated directly from this finite element equation. Most of the secondary state variables, including rate of heat conduction in this case, should be calculated after differentiating the primary state variables, which causes a relatively great error. This discussion can be applied to linear elastic problem in solid mechanics. Compared to the accuracy of displacement, the accuracies of strain and stress can be much lower, which depends on displacement gradient. Of course, we can improve the accuracy of state variables depending on the derivative of the primary state variables by putting additional nodes here and here in this case. Now let's consider again the finite element predictions using this approximated lumped mass system from standpoint of finite method. Its element equation is written here. The elemental force components are depicted in the upper side of this lumped mass system. We can calculate rate of heat conduction in an element from the predicted nodal temperatures, and the results are written just on each element, here, here, and here. We assume that there may exist nodal layers of heat transferring from nodes to environments or boundaries, that is, delta Q1, delta Q2, delta Q3, and delta Q4. Of course, we know that delta Q2 and delta Q3 should be 0 if the predictions satisfy the law of energy conservation, because we assume that the heat transfer in this problem is one-dimensional. Now let's check it. At node 2, the incoming heat flux is 3 plus 11 plus 12, that is 26 over 4 times 3 to the 4th, which is the same with outgoing heat flux, implying that the law of energy conservation is perfectly satisfied, even though there is a distinct difference in temperatures law between these predictions and this exact solution. The same discussion can be applied to the node 3. Please check it. To keep the energy balance in this steady state problem, delta Q1 should be the sum of this and this term, and delta Q4 the sum of this and this term, which are 1 over 12 and 1 over 4 respectively. These values imply that we can get exact solution of rate of heat conduction at the exchange bound conditions. If we rely on the slope at the bounded nodes to calculate the rate of heat conduction, this term in the left side and this term in right side will contribute to the error. In this slide, we are going to evaluate the finite element solutions in terms of slope affecting the rate of heat conduction. Of course, we can see quite great slope error between finite element solution and the exact solution, especially at the nodes. The total heat generation per unit time should be 1 over 3 because the heat generation term is fixed under the steady state condition. To the contrary, we rely on the slope of elements defined by boundary nodes to calculate rate of heat conduction towards environments. We obtain 16 over 81 for it. The detailed procedure of calculating the slopes at both the ends are explained here. The percent error of total rate of heat conduction at the two boundaries with respect to the generated rate of heat amounts to almost 41%. Yeah, it is quite great. This quantitative evaluation emphasizes that the accuracy of secondary state variables depending on derivatives of the primary state variables should be much damaged, even though the final solution satisfies the principle, that is the law of energy conservation as a whole, as we already checked it by distribution in the previous slide. Of course, it also emphasizes the importance of finite model because we can improve the accuracy with each, not only by placing nodes at their optimum position, but also by increasing number of nodes as can be seen here in this figure.